Digipower is a company, is an innovative company which was born as a University of L'Aquila spin-off, and after some years, since 2017, the university left the company, so now it is a completely independent company. I did not discuss it with Ganesh and all other colleagues about the content of this talk, but I understood that it is a seminar from one side, and from another side is a way to introduce the company to the students so that they can evaluate this company for their internship. So first, let me say that our main expertise as a university professor and researchers, and also with the company activity, we are very focused on multi-level power converters. I am not sure about students' background, so I will try to be as simple as possible, but explaining the main features of multi-level converter, and then I will show what we are doing, what we did, and what we are doing at Digipower. But I assume that the students have a quite standard background in electrical, electronic engineers, control engineers, and they are master students. So if there are something wrong or unclear, please stop me, then I can address your issue or your question. So let me say with a very flat start. During the last 2 decades, we had due to global warming and pollution, we had the need to shift from conventional energy produced with fossil fuels, with coke and others, to electricity. Therefore, the electricity is now considered and will become probably the only, or for sure in a few years, the main energetic vector. And for this reason, power electronics converters are becoming and will be more and more important, because power electronic converters are those equipments capable from one side to adapt the electrical energy available at its input terminal in a more appropriate form, with the expected characteristics expected by load, and because they have almost unique capability to manipulate the electrical energy in input according to some very simple or complex rules, which are defined through a control algorithm. Therefore, they are something capable to transform the input energy in the expected energy through a current system, in modern system, to a computer, more in detail, to a microprocessor, or more specifically a microcontroller, or a more complex digital system, such as FPGA, field programmable gate array, or CPLD, complex programmable logic device, or similar digital devices. They are fundamental for using renewable energy, because renewable energy has a high level of fluctuation. Therefore, they are almost impossible to be used in all application with all loads, because application needs stable and very high quality input energy. But they are very important also for smart grids, because with the introduction of more and more electrical loads on the grid, the grid becomes very weak and is subject to problems, to variation of the electrical quantity, then the current and the voltage on the grid, affected by many different kind of disturbance. Therefore, in order to have good operation, stable operation, good power quality, good energy available to loads, it is necessary to adopt intelligent, then smart devices. And smart devices include, in all cases, electronic power converter. So they are fundamental for the transition from the conventional transportation to electric transportation, because electric transportation requires a huge amount of electrical energy, introduce a very high number of new and very complex load requiring a huge amount of energy, each one. Therefore, it is important that the grid is controlled in such a way the electric energy is available to all electric vehicles with the necessary quality. Inside the electric vehicle itself, there are many power converters. Until now, they have a very low power, in many cases below 1 watt or even less, or some watt, because they are used in almost all actuators inside a modern vehicle. But in electrical vehicle, they represent the main part of the vehicle due to the presence of an electric propulsion system which is supplied by battery, which are charged by the smart grid or the grid. And from the other side, they have motors which are supplied through the power converter. So let's go more in detail on the topic of this presentation, of this talk. One of the main problems with multilevel, with power converters, and particular in high power application, and according to general consideration, electric vehicles are very high power loads. I remember that about 20 years ago, not more, 20, 22, 25 at most years, I found a market analysis related to electrical drives, and 20 years ago, 98, I think, % of electrical drives were below 10 kilowatts. Sorry, 10 kilowatts. So, according to this analysis, during the last 20 years, the power level of electrical drives have grown very, very quickly and very seriously. And in electrical vehicles, the standard power rating, particularly in full electric vehicles, are in almost all cases 200 kilowatt or even more. Therefore, they are considered high power converters. But one of the main problems with power electronics is related to the power losses in the power converter. Because from one side, high efficiency means high efficiency for the whole vehicle, and also an extension of the autonomy of the vehicle from one side. But from the other side, if we lose energy, we have the problem with dissipation of this energy. If the efficiency of an electrical system is 90%, means that we are losing, and we need to dissipate 10% of its power. So if the power is 100 kilowatt, we have to dissipate 10 kilowatt, which is not very simple, particular when the space is very limited, as in the case of electric vehicles. And it's very complex if we consider that an electric vehicle, or a vehicle in general, is subject to very different temperature ranges, and often, particularly in some countries, are subject to environmental temperature, ambient temperature, which are over 40 or even more. Therefore, dissipation of 10% of the used energy is a very big problem. In this context, multi-level converter appear as most probably the best solution to improve efficiency of not only of the power converter, then of the power electronic device, but also the whole system for many reasons, because they have some specific capabilities which are not found with conventional two-level PWM inverters. And during the next slide, I will try to introduce these characteristics, giving some background, and then showing some achievable results. Multi-level converters have an additional advantages, including, in addition to many others, which is the high modularity and flexibility, because they can be realized in a modular way. This is a concept which is not so easy to understand for an electric vehicle and should be reached at the design level, not in the practical level. But for instance, if we consider recharging station, then it is possible due to modularity to produce or to install a very different power level recharging station and replace them in case of failures very easily, and so on and so on. So modularity is another very important point in favor of multi-level technology. I'm trying to go quicker because I spent 15 minutes in a very simple introduction. Just to make some history, multi-level converters were originally proposed for railway propulsion system, for high-speed trains, because in this case the power level were well over 1 or 2 or 3 megawatts, and using a standard voltage, it is impossible to reach such high values without very strong losses. Therefore, in order to have megawatts, it is necessary to operate at high voltage, typically some kilovolts. Therefore, conventional converter using commercial devices, which are usually available with a voltage rating not exceeding 1.7 kilovolt, cannot be used to reach the necessary voltage level. One of the main advantages of multi-level converter is that they can operate at low switching frequency, particularly compared to two-level PWM converters. This means that we have very low switching losses because the switching is at very low frequency, even 50 Hertz in case of grid range converters. But in general, switching frequency is much lower than PWM converters. But due to the output waveforms, they have very low harmonic distortion, they have very low harmonic content, then they produce very low harmonic distortion, and this means that we can eliminate bulky and expensive passive filters. In the case of electric vehicles, apparently this is a secondary advantage, but if we consider that electric motors are designed considering sinusoidal voltage and sinusoidal flux and so on, And this cannot be achieved with PWM converters operating at 2 levels. With multi-level converters, we supply the motor with a much better voltage waveforms and with a much better current waveform and at low frequency. Therefore, we have two advantages which are not, which do not interfere each other. So the high overall efficiency of the converter and of the motor are better than with conventional solutions. This slide shows a comparison between the left waveform, which is a conventional PWM waveform, and a typical multi-level voltage waveform. At the bottom, there are the two harmonic spectrum of the PWM, two-level PWM, and the multi-level converter. I want to specify that this particular type of multi-level waveform is a 9-level waveform. In fact, if we count the stairs, there are 9 stairs, including the 0 level. And this is a specific multi-level inverter modulation with overlapped PWM. But as I will show you at the end of this presentation, we are capable, and they are very convenient, to generate waveforms with a fundamental frequency. So instead of having a PWM embedded within the multi-level waveform, we have just a simple staircase waveform. But if we consider these two curves, we can see that with PWM, conventional PWM, we have a 60%, almost 60% total harmonic distortion, while with this not very sophisticated 9-level inverter, without using filters, we have 13% of the total harmonic distortion. You should look to the number, which is very small, but these circle are highlighted the total harmonic distortion. And in this case, we have a magnitude which is 25% in the left graph, while in the second graph, in the right graph, it is 0.6%. So apparently the right part is worse than the left part, but the scale is very different. So this is more or less noise, while these are through harmonics with relevant influence on the behavior of the converter and of the load. So this slide shows a typical operation for a power converter. The bottom left waveform are typical of a conventional 2-level converter. In the case of 3-level converter, where we introduce a more or less phantom neutral point, we have that the voltage goes from 0 to VDC and minus VDC. So we have 3 levels. But adopting a multi-level architecture, we need multiple DC sources, and this leads to generate a staircase waveform. I want to highlight here, and then I will go much faster than now, that this requirement that we need multiple DC sources is a problem with the converters supplied by the grid, where we have just one power supply, or at most 3 in the case of 3-phase line. But in the case of electric vehicles, we have many battery cells, and these battery cells are usually assembled in a very large battery pack with 100 or 1,000 battery cells. So it is very easy to split this high number of elementary battery cells in a subset and then use each for supplying one of the part of the modular multi-level converter. This means that in this specific case, and this is a very great advantage in electric propulsion, we don't need any additional power supply from one side, but from the other side, this required arrangement of battery packs relax the battery system from many problems, because we have very small battery packs which are connected to the converter. They can be easily replaced. Their efficiency is much better, and they are also safer, both because they are smaller and also because each one has a low voltage. Because I did not say, but in all cases, the voltage as the output voltage at the same level. So in this case, the converter and then the motor is supplied switching from 0 or from minus to plus 0. In the case of multi-level inverter, we have very low voltage steps, and increasing the number of levels, we decrease the amplitude of each step. This means that the motor is supplied with not only with sinusoidal current or with pseudo-sinusoidal current, but also with pseudo-sinusoidal voltage, because increasing the number of levels and then decreasing the voltage level, we apply very small voltage step, low voltage step. In order to implement all these, we need to identify and then to develop or to use a hardware architecture. This hardware architecture is strongly dependent on the control algorithm, because it is obvious from my previous work that if we do not have a very good and very specifically developed control algorithm, the hardware itself is not able to do nothing. But the core of multi-level converter is the modulation algorithm, because the modulation algorithm is the part of the control algorithm which is capable to transform the reference signals generated by the control algorithm in specific commands for the hardware system. Of course, as in all other power converters, we need several auxiliary parts, and mostly they are sensors from one side, necessary to monitor and to control and to avoid failures, then to control the temperature and some other important parameters, not only those necessary to implement the control algorithm. And also we need a very fast and powerful communication system, which is necessary to coordinate the propulsion system with the rest of the vehicle, and then with information coming from other sensors which report to the power converter, which is more or less the core of the vehicle. All those information necessary to, for instance, guarantee the correct trajectory in the car, accelerating or decelerating the motor, and so on. Now I will go very fast, because this will be subject of my lecture. I did not mention that I am one of the teachers at the University of L'Aquila, and I will be a teacher in power electronics and electrical machine and in other courses. So I will go very quickly just to give you some idea. Multi-level converter can be classified according to their topology, so according to the way the transistors are connected each other. in some different categories. One is usually known as neutral point clamped inverters or converters. Another is called the flying capacitor, and a third is called the cascaded edge-bridge converter. Then, particular if the power is high, there is a further classification in modular multi-level converter, where each module can be a subset of a previous basic topology. And then, in this case, there are some other issues which I will avoid to introduce here, necessary to make the system really modular. Because while it is quite obvious and easy to understand the concept of module for an hardware system, it is more complex when we consider that this converter is the sum of hardware and software. Therefore, modularity has a significant impact also in control algorithm and particular in modulation. As a final observation, in addition to the basic and more or less classic topologies listed above, there are, particularly during the last few years, many proposals for variants which basically try to reduce the number of devices, maintaining the output characteristics and the efficiency of the system. So these are the form of a typical edge bridge. A typical converter, a typical inverter consists of three of these modules connected in parallel. In this slide, we can say that according to the applied voltage and the signal S, which is the command signal for the transistor, we can have the top level transistor in conduction if we apply S1 is equal 1 and S2 equal 0. Or we have the minus voltage applied to the load if the voltage is applied to the bottom level transistor with the transistor command S2 equal 1 and S1 equal 0. I think that for you is very easy to understand that it is not possible to apply signal 1 to both S1 and S2 because this results in a short throw, because the current will not flow across A and then the load. The load is connected, for instance, between A and another similar leg, B and C and so on. But the current flow across the two components. And as we can assume that the resistance of the transistors, I call transistor, but they usually are MOSFET or IGBT, which means insulated gate bipolar transistor. And then the system goes in short throw. So these are the basic arm, the basic leg of a two-level converter. For neutral point clamped converter, we just put two of them in series, and then we put two capacitors in series in order to have a medium level voltage in the middle of the two capacitors. So in this way, we have more or less created two virtual voltage sources, each one which has 1/2 of the applied voltage. And in order to maintain the system working, it is necessary to add these two clampy diodes, which clamp the neutral point to these 2 points, so that the output voltage can assume the waveform shown in this figure. And with this hardware topology, applying a right sequence of signals S1, S2, S3, and S4, we can obtain the this circuit in the left part, or this circuit in the right top, or this circuit at the bottom, and accordingly the voltage applied to the load is the red line in this with this configuration, the 0 with this configuration, and the minus voltage with this configuration. So, for instance, we can design a 5-level neutral point clamped converter in this way. So we need 4 capacitors. Of course, if the voltage through DC is the same of previous case, in this case, each capacitor is subject to 1/4 of the voltage of the previous case of the voltage DC, then 1/2 of the previous circuit. This means that also this transistor will be subject to lower voltage, as shown in this figure. Therefore, increasing the number of series connected transistors, we can obtain a better waveform, so a higher number of levels. The number of levels can be increased as much as needed. In this way, each stair becomes smaller, but the waveform becomes more complex and more similar to a sinusoidal. This is a clear advantage not only for the load, but also for the power supply, because this means that the voltage, the voltage derivative over the time are smaller, and then the system is affected by less solicitation and becomes more robust. This is another advantage of multi-level technology. It is that even if the system is more complex, the solicitation of this system are much lower, and then the overall reliability of the system can be, if the system is very well designed, much better than in a conventional system. So I will go very fast now, because otherwise we need 2 or 3 hours at least. So there are many other topologies. For instance, the flying capacitor is a very simple and effective solution, but its performance are a bit more difficult to be achieved, because basically we have again the capacitor in series, but with this topology, with the flying capacitor, we eliminate the previous diode. Here we have this diode. Here we have a capacitor in replacement of diode. So the system is much simpler. But the control becomes more complex, because there are energy shift from one capacitor to another. So it is more subject to resonance phenomena, potential resonance phenomena, and then it is more complex to accomplish in practical cases than previous. But of course, it's much cheaper. So, for instance, this is a 5-level flying capacitor. So you can see that we just need three capacitors in replacement of the numerous diodes necessary with the neutral point clamped architecture. This is the truth table for the flying capacitor. I go very fast with this. I can share this slide. Another very common and popular and powerful topology, I prefer this, is the cascaded H-bridge topology, which is very suitable for modular converters. In this case, the best module is a H-bridge. If you have already attended to a course in power electronics, you know that H-bridge is very common also for DC to DC conversion. But applying a voltage, a DC voltage in the input, putting some of them in parallel and in series, and adopting a special modulation technique, we can generate alternative waveform, and in the case of multi-level converter, multi-level staircase waveform. So, for instance, this is a 5-level inverter with 2 edge bridges connected in series. As you can see, these are the input terminals. The central part of the edge bridge is usually connected to the load. In this case, one of the terminal is connected to the upper terminal of the load. Then the other terminal of the edge bridge, the other output of the edge bridge, is connected at the input of the second edge bridge, and then the output of the second bridge is connected to the load, as in this case, and we achieve a 5-level inverter. But we can add additional edge bridge, so we can replicate this scheme, obtaining a high number of levels. Cascaded edge bridge converter, as in this case. As you can see, this edge bridge is connected to this, then this is connected to this, and so on and so on. These are some evaluation regarding the number of components necessary with various topology. Modular multi-level converter are not very complex concept. Is not a very complex context, because we have some standard modules and they are designed and realized in order to be very quickly assembled in series, but we can also assemble in parallel. So if we have some high power demand, we can, in addition to put the module in series, to put some other module in parallel. Of course, each module must be paralleled with another one. This is one constraint in the case of paralleling, and the characteristics, the specification, and the behavior of the module put in parallel must be exactly the same. Otherwise, we will introduce some circulating currents. So they are very powerful, but they need some special attention during design. So let's go ahead. This is a typical architecture of modular multi-level converter. I will try to reduce the size in order to show the whole slide. So this is the basic architecture, and in this case, the basic module is a half bridge, but the basic module can be also a edge bridge or eventually another alternative topology. This is, for instance, the case of edge bridge modular multi-level converter. So basically, making an analysis of current literature, it is possible to identify at least these different basic cells for the modular multi-level converter. This is the edge bridge, is the half bridge. This is an alpha bridge, asymmetrical alpha bridge, where in order to make the system cheaper, one active bridge is replaced by a simple diode. While these are neutral point clamped or flying capacitor based module cells. Now, after this very quick description of hardware, we move to control of multi-level converter. From this point of view, I can see I am quite sure to say that the control algorithm in terms of, for instance, control of dynamic performance of the motor supplied by the multi-level converter are almost the same of the drive where a two-level inverter is used to supply the motor. I mean that if, for instance, we implement vector control for the electric motor, I don't know if you have already studied the multi-level vector control of AC motors, but this is the most common control method for controlling the voltage, the current, the torque of the motor. then the same, almost the same control algorithm without any significant change can be adopted with multi-level converter. This is true because the main difference in terms of control is related to the choice of the modulation technique. Because in a feedback control of a drive, we have the motor in the right part. The motor is supplied by the inverter, but the inverter applies the voltage and then currents to the motor according to the modulation techniques. And the modulation technique is the part which converts the output, the control output, which is a number, which could be also a continuous number, just to not enter in the details, in a discrete state of the power device, of the switch. So the edge bridge, for instance, is shown 2 or 3 slides high. So the modulation algorithm is the link between the control, which can be implemented with a huge amount of different techniques and are independent on the modulation. Of course, there are control which could be better than others, but there is not a strict relationship between the outer loop control and the modulation techniques, which usually, or in many cases, in most of cases, are open loop control. They do not have a feedback, or at most they have an internal feedback. So the feedback of the modulation do not influence the feedback in the mechanical quantities, which are completely independent from the modulation. So the modulation techniques for multi-level converters are the most important part, the most characteristic part. And the modulation are divided in fundamental frequency modulation, which means that the motor, in our case, is supplied by a voltage staircase where the frequency of this staircase is exactly the same required for motor operation. So if the motor must be supplied with the sinusoid at 50 Hz, we have the waveforms which replicate a 50 Hz staircase waveform. If we need 100, we have 100 without any high frequency modulation. And these basic fundamental modulation are usually divided in 2 distinct approaches, are synthesized, adopting 2 distinct approaches. One is harmonic elimination and another is harmonic mitigation. With the first approach, using mathematical formulation, we are capable to completely eliminate some harmonic signals. While with mitigation, we do not eliminate a specific harmonic, but we reduce the value, the amplitude of almost all harmonics. While high frequency modulation are more or less PWM modulation, and they are divided according to the adopted techniques in phase shifted pulse width modulation, or in level shifted modulation, or in space vector modulation. I think that we have speaking since 45 minutes, so I will avoid to enter in details, but according to the choice of modulation, we can improve many factors. For instance, we can improve converter and motor efficiency. We can improve the response rate in terms of control of the speed of the motor, or we can control the limit. We can control the waveform of the current and so on. So this is the most important part in all inverters, and in particular in multi-level inverters. So I move very quickly. This is just, I stopped here just to show how it does work in the case of fundamental frequency modulation for a 7-level inverter. Basically, the modulation algorithm compute, then identify the value of this angle alpha 1, alpha 2, and alpha 3, so that the output voltage of the inverter is represented by this waveform. And as you can see, this waveform is with some degree of approximation and interpolation of the expected sinusoidal waveform. So the modulation algorithm compute the exact value of alpha 1, alpha 2, and alpha 3. Then we have many variants because in this case we have a symmetrical modulation, but we could also have an asymmetrical modulation. So depending on the choice, we can improve some factors and maybe make worse some other factors. This slide is a slide showing an experimental result. So using a microprocessor or an FPGA, as in this case, we are capable to generate output waveforms, which are like the one this shown. The blue line represents the voltage of the output voltage of the multi-level converter with the 13 levels, so with the 6 H-bridge per phase. And the red line represents the current. As you can see in the right part, applying this voltage to the motor, the total harmonic distortion is very, very low, 5.5%. This means that the system has very high efficiency. And the bottom slide shows the fast Fourier transformation, so the total harmonic distortion. And applying this voltage, the sinusoidal has a very good quality because the left line, this I am showing in the left, represents the fundamental frequency, and all other harmonics, so the noise, are very, very limited in amplitude. There are many techniques which allow to improve one or more parameters. So I go very fast. For instance, this is the level shifted PWM. If you know the concept of PWM, to generate a PWM, it is first generated a triangular waveform with a frequency much higher than the expected frequency. So in this case, for instance, we have a maybe 50 hertz sinusoid, and the waveform, the triangular waveform, is 500 hertz. But usually the ratio between the fundamental frequency, the expected current frequency, and the modulation frequency is at least 100, 200 times. So the triangular are very, very small in comparison in terms of time, the time axis in comparison compared with the sinusoid. This means that we apply this voltage waveform, the bottom part, to the motor. So applying this modulation, the motor is supplied with this voltage waveform, and the frequency of these steps is usually in the range of a few kilohertz. Another technique which is quite complex in terms of mathematical formulation, but once solved, the mathematical problem can be easily implemented using a microprocessor, then it's very suitable for digital implementation, is this. And I think that we can move ahead. As I mentioned at the beginning, we can also have many different variations of the topologies capable to reduce the number of devices. Multi-level converter, as all other converters, can be designed using silicon devices, so conventional MOSFET and IGBT. They are very well known, and they allow us to reach 100 kilowatt power but they are usually considered, particularly if they operate at high frequency, affected by high switching losses. Recently, and now they are used in some innovative inverters, have been introduced silicon carbide MOSFET. Their voltage rating is equal or better than standard silicon devices. And until now, commercial devices are for high power, so they operate at high voltage, 1.2 or 1.7 kilovolts, and 100 currents, 200, 500, probably even more. While gallium nitride MOSFET are the latest generation of devices. Until now, their voltage rating is quite low, but during last 2-3 years, the voltage level reached 600, 650 volts. And until now, their current rating is limited to some tenth of ampere. But they have much better characteristics than the others, and are very, very small. I did not include it here some slide showing a comparison of the case of a conventional transistor and the gallium nitride MOSFET. But it is a very small. It's very small compared to a conventional conventional device, because its efficiency, intrinsic efficiency, is much higher. So it is very promising technology for high performance powertrains, particularly using a multi-level converter, because they can be very, very compact, and the limited voltage can be easily overcome by the high number of levels. So, in my opinion, this will be most probably the future of high performance drives for electric propulsion. So now I will show some of the activities already done at Digipower. This system I'm showing is a 1 megawatt power converter. It is a demonstrator which consists of up to 48 cells. This means that if we use all these cells in series, so the system is clearly a modular multi-level converter. So if we put all cells in series, we can reach 97 levels. This means that this system, operated with 600 volts on each edge bridge, can reach 20 kilovolts. So the typical application of this system is in a smart grid or in a renewable energy, for instance, wind power generators. But all studies and all concepts identified and developed for this application can be very easily adopted in designing and realizing electric powertrain for electric propulsion. And this is one of the activities. It is the most, the current most interesting study we are doing at Digipower and at the University of L'Aquila ICT for Energy Group. So this is a basic layout of the system. All these has been designed and realized at Digipower. The system, as already said, consists of 48 cells. Each cell is designed here with a small block, and then in our typical case, they are arranged in a three-phase system, and all these cells are coordinated and controlled by a single board, which is shown in the middle. This board, in this figure, the left part represents the top layer of the control board, while the right side represents the bottom part of the same board. So this board, which is detailed, which function is shown in this slide. Let me move this one. Control the whole system. One moment. Okay. So the board includes an FPGA, which is the most powerful digital control, a digital device suitable to implement almost all control algorithms in hardware. I cannot spend time in describing FPGA for those of you which never listen hear about it. But this board is controlled by an FPGA which has two coprocessors. One is a TPLD, which in this application is a simple bus extender, and it has been introduced to adopt to use a cheap FPGA and at the same time have enough pins to control 48H bridge. And then there is a DSP, which is very typical in electrical drives. And then it allows to implement already developed algorithms, which usually are developed using C language, while FPGA must be programmed typically using a hardware description language, which is usually known as DHDL language, which means hardware description language. So this board includes some communication channels. In particular, there are 48 bidirectional channels to communicate independently with each cell, but also include an Ethernet interconnection and serial interconnection, two serial interconnection. It has also a small display. It is shown here in the figure. And just to show capability of this system, we have implemented a 25-level modulation, and these are the voltage and the current outputs from this system. But this waveform is obtained limiting the use at 12 H-bridge only, because the rule to obtain the levels is that if you have L H-bridge, if you have N H-bridge, the number L of levels is equal to multiplied N plus 1, and this is very obvious and is simple to verify it. So as at Digipower, we have just 12 programmable power supply. We limited our experiment to 25 levels. But to make other tests, we have simpler but not very powerful power supply. We need the 48 power supply. You should consider that programmable power supply is quite expensive. Then we performed most of tests using a simple fixed voltage power supply, and with this we are able to obtain 3 33-level waveforms or 1 97-level waveform. This slide shows some details of the H-bridge. As you can see, they are built with a modular approach. So it is a module built with modular approach, very simple. So it can be easily replaced, repaired, improved, and each module can be used also to design, for instance, neutral point clamped or flying capacitor architecture, not only H-bridge cascaded for a cascaded H-bridge architecture. And each H-bridge is intelligent, is smart, because it has its own DSP. This board are the driver module are vertical with this arrangement. Then this H-bridge has a power level which exceeds 20 kilowatts at 600 volts. This is a detail of the board. I am out of my time, so I just show a magnified board. The central square device is the FPGA. This other smaller is the TPLD, and this is the DSP, while this is the display, and this is the serial connector. While in the opposite side, in the rear part of the board, there are the 48 connector to interface the single H bridge with this board. This is another view of the system. We have designed and realized some different demonstrators, but now we are focused on using 9-level three-phase systems. We implemented control, STATCOM control, as in this scale. The system can be easily adapted. It is just sufficient to change some bridge, some wires, and change, of course, the software. It could be used for photovoltaic generation. In the left part, we have this show in this figure. We have 12 PV panels, and the conventional inverter have all these parallel. These panels connected in series in parallel, so there is only one input to the inverter, and then the inverter is a three-phase inverter, inject energy to the grid, but it needs a passive filter, and usually, according to literature, the best option for output filter is an LCL filter, which include 3 inductors at top, 3 inductors at bottom, and 3 capacitors. This is expensive because inductors are realized with pure copper, and capacitor should have a high value, and then most probably are electrolytic capacitors, but electrolytic capacitors are very sensitive to stress, and then must be replaced after 10,000 hours, and could be the main cause of the failure. While with multi-level inverter, we can simply connect one panel to one H bridge, the other panel to another H bridge, and so on and so on. And then the output voltage of the inverter are sinusoidal, as I've shown. Then we don't need inverter, we don't need a filter, or we need just a light filter with a very small inductors, because it is necessary to eliminate high frequency signals. And this scheme is exactly the same we can use for an electric vehicle, where we can consider, as already mentioned, the battery pack split in 12 distinct battery packs, as shown in this figure, and then we can move to this application, where from a conventional drive for electric vehicle, we can move to a multi-level converter, and of course we need additional bidirectional converter for recharging the battery. But also in this case, for sure, we need more converters, but their power and their voltage and their current, particularly their voltage and power, are much lower than in the case shown with the conventional converter. We did some study to compare different solutions, finding that a 9-level inverter is better for battery, is better in terms of total harmonic distortion, and of course torque ripple, because applying a better voltage and current waveform, motor torque ripple is much lower, as shown in this figure. And now, just to close my talk, my pitch, we are working as a university research group on the design and realization of electric propulsion system for aircraft. Recently, we participated to a European Commission call, Clean Aviation, with some partners in Europe, with the idea to develop multi-megawatt power converters for whole electric aircraft. And currently, we are cooperating with IIT, Italian Institute of Technology, which is the premier research institution in Italy, for designing multi-level drives and recharging systems for cobots. Cobots are, as the one shown in the right part, robotic system where consisting of a moving platform with hosting battery and moving a robotic arm, which purpose are numerous, is very various, but they simplify the life, human life inside a factory, replacing a human or cooperating with a human in some hard work. I can finish my presentation. I think that the conclusions are clear after listening my talk. This is the place where now is the Digipower. Is a cottage in front of Gran Sasso Mountain. It's a very nice place where you can see mountains. We have enough space for hosting students which are interested to developing some of their activities like thesis or simply internship during E-PiCo project. So I thank you for your attention and I'm waiting for your questions.
Okay, thank you, Carlo, for this well-structured and nice talk about multi-level converters used for mainly renewable energies, okay? And,
yes, I think that they are very suitable also for power train. So now we are working on this, not on renewable energy.
Yeah, okay. So thank you for this.
Yes, of course, they are useful also for recharging stations.
Yeah, of course. Yeah, it's very, very interesting. It's well connected with e-propulsion, yeah.
Mm-hmm.
Okay, yeah, our students, if you have any questions to Carlo, so it's a time to ask him.
Professor, I want
Yes.
to ask something.
Yeah.
Thank you so much for really perfect information about converters. You know, actually, it's obvious that multi-level converters can provide many advantages because they can provide a better signal waveform for the motor. And if we consider the life cost cycle, of course, in the long period, it prevents the bad effects on motor, and also it brings many advantages for electrical vehicles. But I think personally that maybe some companies are reluctant to use high levels because it's obviously it can be heavier, it can be more expensive, and of course the controller can be complex. And what I want to know is that in practical, in companies, especially in car companies, car manufacturers, which type is most common? How many levels they usually use? Because based on what Mr. Ludo from Renault talked, I thought maybe it's not really common to use high levels of converters. I just want to know what's happening in reality.
Yes, let me say, until now, in my knowledge, multi-level converter are still used in some specific application where the power level are around or over 1 megawatt. But they are not yet used in lower power application. I had some contact with companies, at least in our area and also in Europe. They try to limit the number of levels to 3, 5, or even 7, so quite low level. But in my opinion, this is not the best choice, because I think that you have clearly understood that from the load side it gives many advantages. From the converter side, it has more devices from one side, but from the other side, the stress of each single device is much lighter than in the case of a conventional converter with the same power level. So if you have to supply a vehicle motor which is 200 kilowatts, for instance, in one case you have to turn on and off 600 or 1.2 kilovolt transistor at 20 kilohertz, 40 kilohertz. In this case, you have some transistors which have a lower voltage and commutate switch at low frequency. So the stress is much lower also for the power converter. The problem of the cost is, in my opinion, not very well conditioned, because it for sure is more expensive in terms of development, knowledge, as I can see, in optimization and so on. But once the system and this has been well designed, well tested, then you can for sure use devices which are much cheaper, because one transistor which commutate 500 ampere at 1.2 kilovolt is expensive, and while if you use, as in our case, conventional very cheap transistor commutating 100 ampere at 200 volts, they are much cheaper. So the total cost of the transistor is lower. The total cost of all other parts are similar or lower. The main point is that they need more drivers. Drivers, of course, are corresponding to the transistor. So if you have 6 transistors, you need 6 drivers. If you have 24, you need 24 drivers. And the cost of the driver is similar if you drive one big transistor or a small transistor. Depends on the power level, but there are some boundary where more or less the cost is very similar. So this solution is more expensive. But if the voltage level and the power level increase, this is not true, and probably they are more comparable.
Okay, okay, thank you.
But I believe that once this technology become industrial mature, the company like Infineon or other similar company can integrate in a single chip, as they already done for many very large markets for consumer electronics drivers in the same chip. So while now the cost is because you have to buy 24 chips, then put a capacitor and so on and so on, I am almost sure that the complexity of a board can be reduced with integration. And integration has not a technological problem. It's just a market problem. If nobody will push company to produce integrated drives for multi-level converter, of course they will be very expensive. But if the industry push silicon company to produce drivers for multi-level converter, they cost exactly as for a single multi-level converter. I can just say a simple observation. Infineon, I cited now it, 1 year ago, I think, introduced a single chip audio amplifier with multi-level technology. And the cost of this chip is almost the same of similar digital audio amplifier, integrated audio amplifier produced by competitors. The quality of the sound, the efficiency of the system, I never listened it, but reading some blogs and some comments are better than with competitor realized with the standard PWM digital audio amplifier techniques. So this is, in my opinion, one clear demonstration that if a company, a big company like Infineon, believe that the market can accept the product, they have no technical issue and no economic issue to produce components with multi-level technology. So I expect that in probably 5 years, 10 years at most, they will replace conventional two-level inverters. This is my convincement.
Of course, maybe in first glance, it seems to be expensive, but if we consider the really bad effects of harmonics and other effects
Yes,
on the other device in long period, of course, it makes sense.
Yes, I'm sure. I am happy that you have fully understand this, but I believe that in long term also the cost. On the other side, I am quite now old. When inverters were introduced 30, 35 years ago, the discussion was among six-step inverter and PWM inverters. So now, if you buy a toothbrush, it has inside a system controlled with a motor controlled by PWM technique and the cost below €1. And nobody, I think, consider to develop a six-step inverter in any application.
Okay.
So I think that this is my answer. There are no other options.
Okay. Okay. Thank you so much.
The option will be in introducing at commercial level, then in industrial product, reduced count in multi-level topology, because I just mentioned them, but there are many studies during the last 10 years aiming to produce a staircase waveform with less component than the modular multi-level converter. This means that as the system has many switches, not all states, possible states are necessary. And then implementing a specific control algorithm which do not generate unavailable states, you can obtain more or less the same results, adopting simpler topology with reduced count power devices. So, for instance, you can generate the waveform, output waveform equivalent to a 9-level inverter, which needs 24 devices in the case of H-bridge, with maybe 12 switch. So you can reduce, you can cut 50% or probably even more components, obtaining the same output. Of course, you have some constraints to respect. But in some applications, these constraints are acceptable, so do not introduce any real limitation. So it is just a problem of developing the software which offer the necessary patterns for the output for the inverter and to select the best modulation algorithm capable to produce the best waveform with the limited number of devices. So this is now the hot research topic.
Okay, thank you so much, Prof.
Welcome. Ganesh, your mic is not on.
Yeah, now I think it's on. Yeah, thank you for this. So there is another questions. If you have any questions, so don't hesitate to ask them to Carlo. Maybe I have one question for you, Carlo.
Yes, thank you.
Yes. Because I have seen all the kinds, because I'm working since 10 years now ago about multi-level converters, and I have mostly worked on all the type of converters that you have presented here, but I didn't see one type of converter.
Which one?
Yeah, it is a parallel multi-level converter, which is mainly designed by inductances and non-capacitance. And you have the load. The load is a small voltages, you know, which emulates, let's say, calculators. You know, where you have smaller voltages that to be well regulated in calculators. Okay, and on the branches you don't have capacitors, but you have inductances. That is what is called parallel and not series. You know.
Yes.
And
So,
do you work about
my
this kind of converter or not?
no, until now we focused mostly on cascaded edge bridge converter. We addressed almost our efforts in developing a quite reliable hardware architecture. In my opinion, it is very important to have a industrial grade system in terms of integration between the control system and the power inverter. So we did not consider to use, for instance, DSpace or Opal RT or Typhoon or similar commercial devices, because while they are very much simpler than our system for developing control algorithms, apparently, they introduce many constraints and problems in interconnecting the control system with the power system, and then to make a reliable system from one side and to the other to eliminate all possible disturbance in implementation of the control. And then we worked and we are working on modulation, and we now are working since several years on fundamental frequency modulation. In my group, there are Professoressa Bucella and Professoressa Cimoloni, who are now very, very expert in developing algorithms, which are analytical algorithms for solving the modulation problem, then to compute in real time with very limited computational resources, all angles of complex multi-level converters. This means that we did the choice to focus on edge bridge. Otherwise, our results, which are very complex to achieve, were not available. My group is very small, and then we have to focus on a specific topic. So we focused on edge bridge, multi-level cascaded edge bridge, and on fundamental modulation algorithm. Of course, we implemented many other modulation algorithms, for instance, level shifted, phase shifted, and many some different vector multi-level vector algorithms for multi-level converter. But we did not spread on different topologies. In all cases, I think that, as I said, with modular approach, you can parallel different modules, and with control, balance the voltage and then make the system with the parallel modules efficient as with a single module in parallel. So the power level can be increased, not only increasing the number of levels and reducing the voltage rating of the transistor, but also putting module in parallel. I did not mention that our edge bridge are more or less universal in the sense that we can also then we can replace MOSFET with IGBT with very different voltage and current. So more or less the same edge bridge can control up to 20 kilowatts, but with a different voltage and current. If you adopt low voltage MOSFET, you can obtain with a single component 200, 300, or even more ampere. But of course, with the voltage, applied voltage, that with the voltage step, which is 40 volts, 50 volts. But on the other side, if you consider our application, vehicle application, usually the voltage level do not exceed 400, 500 volts. I am not very familiar with commercial products, but I believe that most of current electric vehicles, including Tesla or Porsche, have voltage level not over 600 volts or 700 volts. So using a multiple multi-level system with 9 level or similar number of levels, you can realize very powerful drives without paralleling power devices, and this makes system cheap, simple, and very reliable, because one of the main problems with the power converter comes when you put a component in parallel, because components are not exactly equal, therefore there are very easy imbalance due to the slightly different resistance or turn on and turn off. And then if you use only one device for each edge bridge, so one switching for switch for a edge bridge, each one is controlled independently, the reliability is the best you can achieve.
Yeah. So,
but of course, if we speak about research, we can discuss about your and we can try to cooperate and implement some system using your background, your algorithms with our system, maybe making some modification. The fact that we have developed everything make us capable to modify, to adapt, to improve, to replace, to repair very quickly.
Yeah, so thank you for this all comments from the multi-level converter side. So yeah, just to assure our students, so they be sure that all these multi-level converters are used on stationary applications, which are not mainly embedded solution. You know, they are now the ongoing work, okay, on these applications, and there is a big link between electrical vehicles and electrical vehicle charging, okay, by using, as said by Carlo, renewable energies, and in general, yeah, the power coming from renewable energies is high, and it's better to use multi-level converter than conventional converters in order to to transform the energy to a suitable energy for charging electrical vehicles. So I think they are very, very important in this field.
Okay, and of course I will be glad if some of additional students or students will come at L'Aquila and will be interested in developing some activity in this field.
How many people are involved in your company, Carlo?
Now nobody, because some of them got a new job 2 or 3 months ago, and so now we are going to rebuild a team. Until few months ago, 2 months ago, we were about 9-10 people. But now some PhD student will be graduated. One was hired by a German company in North Italy. Another joined Pirelli, two of the main employers changed company, went to a big company. The problem of spin-off and small company is that turnover is very high, and this is a lot of knowledge and a lot of opportunity for the company. It's a very big problem because people came work in state-of-the-art development and after that capitalize their knowledge and go in bigger company for a higher salary and expecting more success. But often they understand that they changed from the best to the worst. But of course, this is a big problem for a similar company. This has happened other times. So we are considering the business model, more or less.
Yeah, of course.
We have some contact with some foreign and bigger company which could make a joint venture with Digipower, giving the idea that there is a very solid company on the back, and then people work more motivated for their future.
Yeah, I think the students will be happy when they come in L'Aquila to discover your company, because as you said, it's a small company, so you can access many materials and to see how they are really designed, how they are really implemented, and so on. I think this fact is very important. But I don't know if there is a possibility when the students come to L'Aquila to visit your company.
Yes, of course. As I mentioned, my PhD students mostly worked at Digipower because in university we do not have a good facility, and at Digipower they were fully supported by engineers of Digipower. Now, as I mentioned, the main engineer left at the beginning of December, so 2 months ago, less than 2 months ago. So now we are reconsidering how to rebuild a good team. The team which developed the system were consisted of about 12, 13 people. Then we have these laws, because even if you pay good salary to people, typical of salary, they consider a big company more stable and give a better future. And maybe they reduce their responsibility.
Yeah, of course.
This is another point.
Yeah.
They say, even if I do nothing, nobody will claim with me, and the company will survive. While with a small company, the company could not survive, so people prefer. And this is a big problem for small companies.
Yeah, okay. Yeah. So I agree with you, Carlo. So thank you very much, Carlo, for this nice talk. And,
so I welcome as much as possible students, of course.
Yeah, of course. Yeah, they will be, I think, very happy to join L'Aquila and to discover what it is done in this field on your university and company. Okay. And,
good. I also wait you, of course.
Yeah, of course. Yeah, I will be happy when the situation, when the pandemic crisis will be better. Yeah, in the future, I hope that it will be better, and it will be behind us, in order to go physically to L'Aquila and to your company, to visit your company, to see what is really done, and to see what kinds of collaboration that we can
establish. Yes.
Yeah, we can exactly establish together. I think it's very important.
But for students, I can say that L'Aquila has never been a very critical town, in the sense that we had a very limited number of cases of COVID, even now. Just last week, I attended a meeting with the chair of epidemic department at regional hospital, and he said that from the start of the COVID in L'Aquila, they had 400 patients in 1 year, 400. In L'Aquila, we did not have that, I think. So the situation has been always simple. Of course, all of us avoid to attend shop, to go to shop, to attend meetings and others. But this is just because everybody is careful, but not for the real need.
Yeah. Compared to other countries in Europe, so Italy has managed well the situation, the pandemic situation. So, and in Aquila, maybe it was managed better than other places. So,
yes, it's also a small town with a limited number of inhabitants. So, of course, it is a probability problem.
Yeah, it helps. Yeah. Okay.
And also, spaces are much larger. People do not take public transportation. There are no metro and so on. But therefore, the probability to meet infected on your path is very rare.
Yeah. I think the students are well understood these rules, and I think they will be they will make attention to this situation. I hope that it will be okay.
Okay. If there are no other questions, I think that we can close this virtual meeting.